Today we're going to talk about the junctions. How do you make connections on putting systems together? So we'll talk about the zero junction and we'll talk about the one junction and give some examples on how we connect this to the rest of the elements and build up systems. So let's go over here and examine this situation here. This one is a very easy connection to understand. You see, you have in here a pipe, and you have a flow that comes this way and flow that comes this way. So if flow comes this way and this other one comes this way, it's obvious that the output is going to be this way. I think it would be important to make a distinction here. We are talking about either the flows or the efforts, but not both for the connections. This zero junction that we call is for this kind of situation where the flow 1 plus the flow 2 produces flow 3. But remember, what about the pressure here? Let me see how that physics class is in your minds. Can anybody tell me anything about the pressure? Huh? Huh? Remember Pascal's principle? What does it say? For a pipe, a connection like this, the pressure has to be the same, right? The flows will add up, but the pressure is the same. You agree? That's basically based on Pascal's principle, right? On the right-hand side here, look at this kind of situation. You say, oh, this is like when you connect the two loops in parallel in here. Well, yeah. Current comes this way, some current goes this way, and some continues this way, right? Do you remember how is what controls that? What's the name of the laws that control this? In a circuit, that's called Kirchhoff's laws, remember? Yeah. So in here, according to Pascal's principle, the pressure is the same by the flow's sum. According to Kirchhoff's law here, the currents sum. But what about the voltage here? What is it? It's the same, right? For this kind of connection, the voltages are the same, but the flows will add up. That property for the left-hand side means the flows will add and the effort is the same. And in this case, the effort is the same, which is the voltage, but the flows, meaning the current, will add. That kind of connection is known as the zero junction. And in the equation format is F1, F2 is equal plus F1 plus F2 is F3, but the pressures are the same. Or I1 minus I2 equals to I sub 3, but the voltages are the same. If you represent it in a bond graph form, the junction, that's what it means. You see here there's the 1, 2, and 3, which are the efforts are the same, but the flows would be F1 plus F2 plus F3 equals to 0. So that's the property of this junction. Here, if you put the flow to be adding different ways, I put several examples in there so that you can see how this junction works. The efforts in all of them, in all these four, the efforts in all of them are totally the same. See, E1, E2, E3, E1, E2, E3, E1, E2, E3, all the same. The difference is that these half arrows that we have put in here control how the flows sum. So in this case, to read what you have on the left-hand side here, you read that F1 minus F3 equals F2, or you could say that F1, what came in, is equal to what goes out, which is F2 plus F3, right? So that's the point. Now over here, see, you have two of this coming in and one going out. So this means F1 plus F2 is F3. These all three are going out. I put that deliberately because I wanted to show you that if you apply the principle that the flows add up to 0, then it doesn't matter if all three go out. They need to add up to 0. So therefore the same. What I also do is I find it very nicely is to have the convention that anything that comes in is positive, anything that goes out is negative, and that's how I wrote this. Look at this one, all three come in. Same thing. Sum of all three equals to 0. Yeah? Any questions about this? One thing that is unique to these junctions, and it is very important that we are careful about, and we analyze this and repeat it several times, is that when one of the bonds, like in this case, the number 1 sets the effort, all the others have to be out. So the effort is into the junction, all the efforts have to be out. So there can be only one and only one effort input on a zero junction. See, the effort input is here on number 2, and these are outputs. What's the effort input on this one? 3, and the outputs are there. So that's very important to keep in mind. Now, if we add the power flow and the causality the same, we superimpose on each other, we have the complete representation, but basically nothing changed, because you have effort this way and the flows add up the same way as I had before. And here F1 plus F2 is F3. Well, that's what I had before. So it means that the addition of these causal marks has no influence on how things add up inside the junction. This is a summary of these junction properties. It is a common effort junction for all bonds attached. All efforts are equal. The sum of the flows equal to 0. Power conserving. Power in equals to what power out. Only one causal mark determines the input effort, and all others will have to be out. There's only one bond, and one bond only, that sets the effort input. And finally, the power flow half arrows determine how the flows will sum. That's a summary of how this junction is. And I gave you some examples at first in here of real life things on how this zero junction is, as you can see in here. This is the kind of connection in a hydraulic system, which is easier to understand. This is the connection on a electrical system. Any questions about this before I go on? Okay, now we have there was a question there? No? All right. Now we go to the one junction. Now, I have put in there two examples, one on the left and one on the right-hand side, where you have, in here you have the current, you see, it goes this way. And the current is obviously, in this case, is seen by these three elements in the loop. or maybe use a series connection if it's an electrical system. And if you have on the right-hand side a mechanical system, what you have is the summation of the forces. Yeah? So summation of the forces, and in this case you have the summation of the voltages. One question I have for you. In the case of this, when I say summation of all the voltages, what is it? Is it summation of the efforts or summation of flows? Huh? When I say, what's voltage? Is effort or flow? It's effort. So it means that this kind of connection, it means that you have a common flow, but the efforts will sum. Same thing here. You know that the forces will add up, but the velocity of this point as it moves is going to be the same for all the mass and the spring, whatever is connected to it. So this is in this case, you sum the efforts. Okay, you sum the efforts, but the flow is the same. So this is the reverse. You can see here, and I want to emphasize this and perhaps go a little slowly here, that the common flow, in this case the current, is what makes this type of connection. And in this case, what makes the connection be a one junction is because of the current, of the velocities are the same. So let's go over here now and do it in a more technical way, in the bond graph way. So in here you see you have a one junction that connects the three components in there. And in here we say, okay, F1, F2, and F3 are the same, but the efforts will add up. And we don't have the arrows yet, so we just say E1 plus E2 plus E3 equals to 0. That's how it needs to happen. If you make the representation now in the bond graph form, you see this is the one junction, and you say, how do we read this? This says F1, E1. No, first of all, it says F1, F2, F3 are the same. That's what this is. Second thing is saying E1 is equal to E2 plus E3, because what comes in is equal to what goes out. Yeah? And then on the right hand side you have 2 coming in, and then you have 1 going out. So this is F1 is equal to F2 and equals to F3, and then you have E1 plus E sub 2 equals to E sub 3. Now you have in here F1, same thing, the flows are the same, but then you have minus E1 minus E2 minus E3 equals 0, and then you have the summation of those 3 equals to 0. Any question before I go on? Because I think we are at the crucial step of adding the causal marks to this junction. And I want to make sure that everything is clear. There we go. If we have one of the bonds that sets the flow input to the junction 1, all the other flows have to be out. In this case, F1 is the flow input, and only one flow input can be on a one junction. Same thing here. F2 is the one input, and these are the 2 outputs. Here, F3 is the input, and these are the 2 outputs. Any questions about this? we put now the causal mark plus the power flow together. I have deliberately taken the time to make sure that we indicate the flows with red color, and then it says, okay, in this case it says, remember the flows are the same, but E1 is equal to E sub 2 plus E sub 3. That's how you read this picture. So what you're seeing all along is that for the individual elements, the constitutive relationship, or for the individual junctions, or the two port elements, there's always equations associated with the connection, equations associated with the properties of RCs, RTFs, and GY elements. And now we are saying, pay attention to just one more detail. If there's one flow in, all the other flows have to be out. See, in this case, F sub 3 is the flow in, and F2 and F1 are flow outs. On this one, in here, which one is the flow in? F1 is equal to, see, in this case, you can write the equation that F1 plus F2, E1 plus E2 equals to E sub 3. See? So, yeah. Now, what about on this one? See, in here, this is the F1, F2, F3 the same, but all three efforts will add up to 0. And the same thing on this other right-hand side. The flows are the same, the efforts will add up to 0. How do we represent it in the block diagram form? On the left-hand side, you have the notation in Simulink that could be used for a connection like this. In Simulink, you use either the round summation point, as we saw it in the previous example, or in the previous section, or you use this square. So in here, you indicate E1 plus E2 minus E3 is E sub 4. That's what this is saying on the bottom. E1 plus E2 equals E3 plus E4, or E1 plus E2 minus E3 is E sub 4, as we write only one variable to be the output. Same thing on the zero junction over here. If F4 is the output, you can read that you have F1 coming in, F2 coming in, and F3 going out. So you can easily use that convention. Coming in positive, so F1 plus F2 are plus. Going out negative, which is F sub 3. And then is equal to F sub 4. And that's why you have what you have on the right-hand side over here. Summary of this. Summary of the one junction properties. It is a common flow junction for all bonds attached. All flows are the same. Flows are equal. Sum of the efforts equals to 0. Is a power conserving element. Power in equals to power out. Only one causal mark determines the input flow, and therefore all the other flows need to be outputs. There can be only one bond, and only one bond that sets the flow input. And also power flow half arrows determine how the efforts will sum in this case. So the opposite, the reverse as the zero junction, right? If you put together now some connection with some elements, may look something like this, but we are mainly concerned about the connection here is the 0. which means that F1 plus F2 minus F3 equals to F sub 4, and then multiply by 1 over C and integrate it will really come out as the position in this particular case, Q sub 4. You have, for the I element, this is another connection that you can do. We're just practicing the properties of this connection. But what's important to read is, you see here, there's only one flow, which is F sub 4. So the causal marks are the other way. But the effort A1 plus E sub 2 has to be equal to E sub 3 plus E sub 4. So in order to write it in one, with only one output, then you say E1 plus E2 minus E3 equals F4. That's how this picture reads. This is, again, if you connect, you make that connection to the R element or the zero junction to R element. You can connect it to a TF, this would be the representation, or to a GY element. Finally, the last slide of this series is just a summary of the different causal forms. This is the preferred integral form that we want for C elements in here. And this is the preferred one for I elements. But if the other ones, the derivative happens, it happens because it depends on how systems are connected. The TF always this way, the GY always this way. So I hope you get a chance to review these connections and this little summary, and then we will be ready to put together systems as a whole.